Real-time digital signal processing lab class at the University of Texas at Austin. So homework 2 was due, and you turned it in, thank you, and there's a solution set on the back in hard copy as well, and this will be online later today as an electronic form. So the 3 questions on this one, and this one got a little more involved in filter design and application of filters to processing an audio signal. First question is analysis, then we'll move to filter simulation, and then filter design. Those are the 3 questions. So I've included the questions on the solution set, so fire away with questions as usual. So the first question was take the 4 filters from homework, problem 1.1, I'll repeat those filters in the solution set, and do some additional analysis. So in problem 1.1, you found the transfer function, including the region of convergence. So now a little more work. Now we'll plot pole 0 locations. Is it bounded input, bounded output stable? What's the frequency response as a formula, and so forth. Okay, so, and again, these are 5 very commonly used filters. All right, first one up is the averaging filter. And for the averaging filter, it's the version that has 5 coefficients and it's normalized. So we use this 5 coefficient version in the Mandrill demo for image processing on Friday, right, which will be up online shortly. So there's a nice MATLAB command called zplane, and it plots finds the 0 locations and the pole locations and plots them in the z-plane. Right? So here's the z-plane. We have the real part of the z-axis is here, and the imaginary part is up here. And if you remember from the demo, of the Mandrill, with the processing the Mandrill image, it had, if you remember, had 2 0 locations, or 2 frequencies that got zeroed out completely, and those correspond to whenever you see a 0 on the unit circle, remember the mapping from the unit circle to, from the z-plane to the Fourier domain is z equals either j omega, omega equals 0 implies z equals 1. So this point right here when z is 1, which happens right there, as best as I can draw it, corresponds to 0 frequency, and the angle from the horizontal positive real axis to wherever I'm interested in the unit circle is my frequency. It's omega, right? So z equals either j omega. This is a circle of radius 1. Okay. So wherever I have a 0 on the unit circle, it's going to correspond to the frequency of that 0 location. Is going to correspond to a 0 in the magnitude response. We'll explore that more on Friday in lecture 6 slides. So that 0 location, so we have 2 frequencies that are being eliminated. This 0, the 0 there is eliminating a frequency, and the 0 here is eliminating a frequency. And you may recall from earlier homework problems, and you'll see it again on the 4th part of this one, that if I am going to work with a particular frequency value, I'm going to have conjugate symmetric poles and zeros. Okay, so this 0 is the positive frequency, and this 0 is simply the negative one. They're going to come in pairs. So I have 4 zeros. I have 2 corresponding to positive frequencies and 2 corresponding to negative frequencies.
What do you mean by eliminated frequency?
It means exactly that. It means that if this filter, this averaging filter, were applied to an input signal, 2 frequencies get eliminated completely, get zeroed out. They don't get through, however you want to say it. Okay, now the region of convergence includes the whole plane except for the origin, and because the region of convergence includes the unit circle, it's bounded input, bounded output stable. You could also argue, the poles are inside. The only poles that show up here are artificial poles that just simply correspond to, doing an algebraic, just a simple change to the transfer function to make the powers of z be non-negative, and you get these 4 artificial pole locations at z equals 0. So however you want to look at it, lots of ways you can get this to be bibostable. But more generally, all FIR filters, even when implemented, are bibostable. This is a huge advantage for FIR filters. You don't have to worry about bibostability. And again, there's some applications where bibo instability is a good thing. So it's not always what you want. But if you want bibostability, FIR filters will always give it to you, regardless of implementation. Okay, since we can convert this to a frequency response, which we do, and we can use the MATLAB command freqz to plot that for us, plots both the magnitude and phase for us. And we just have to feed it the coefficients, the coefficients of the impulse response, basically, the values of the impulse response. Okay, and we can see the 2 zeros being eliminated. The 2 frequencies are being eliminated. These correspond to zeros in the magnitude response. We've already talked about the phase response when we did the mandrel demo, but this phase response has 2 points of discontinuity, and they correspond to exactly the same points where the same frequency values that are removed by the filter as seen by zeros in the magnitude response. So all these discontinuities are present. Those frequencies are getting through anyway. The slope is still constant over all frequencies. And what is that slope? I didn't ask that, but what is the slope? Oh, I'm sorry. Yeah, that's the next question. What's the numerical value of the slope? Well, this isn't. Oh, we had to get this back to radians to make it more useful. We do this in radians. But you know kind of what it is from the mandrel. What's your guess? It's a 5 coefficient averaging filter. Impulse response is symmetric about the midpoint. Corresponds to a delay of how many samples? I'm hearing 4, I'm hearing 2, I'm hearing 2.5. There is a correct answer in those 3 choices. All right, so the impulse response starts at the origin, is 5 samples long. All right, there's your impulse response. And this is the normalized, so it was 1/5. Right, there's your impulse response. So I start at index 0 and at index 4, which is a total of 5 samples that are not 0. The extent is 5 samples. And the midpoint is at n equals 2. Right, so the midpoint is right here at n equals 2. And now we have an integer delay through the filter, more comfortable than a half sample delay to me, and to some of you who've expressed this. So this is a filter that has a phase characteristic or a phase response that looks the same as the phase response as a delay by 2 samples. Okay, so in terms of how the input signal passes through the filter to the output, there is a group delay of 2 samples, which will correspond to a slope. If we had this in radians instead of phase, we see the slope as -2. As -2. Any questions on the 5-tap averaging filter? Go ahead.
So if it was 6 samples, it would have been 2.5.
Yeah, so if it were 6 samples long, the midpoint would be 2.5. Right, so the midpoint, more generally, is n equals the length. I'll go with n minus 1 over 2. There's your midpoint. Right, so when n was 2, which was the 2-tap averaging filter, the midpoint was 1/2. If n is 6, it's 5/2. And solution sets on the back table. There you go. Now, I made some other general comments, and I made these on Friday, or made these during the video when we did the mandrel demo. But just to repeat it, the averaging filter is kind of useful. The null bandwidth is always 2 pi over n, where n is the number of coefficients. So I can nicely, if I need a very simple to implement low-pass filter, and I don't need any multiplications, because I can just multiply through to make all the coefficients 1. In the averaging filter, I pick my length, n, accordingly. So my null bandwidth is 2 pi over n. And when n was 2, the two-tap averaging filter, the null bandwidth was just pi. That's the first point at which the magnitude response went to 0. Not a terribly great low-pass filter. It gets a little, obviously there's better selectivity with increasing n. That's the good news. Bad news is that the stop-band attenuation is always 13.5 dB, and there's nothing you can do about it, regardless of the number of coefficients you're using. So it's not a terribly selective filter, but it's a simple to implement filter. Easy to implement. So, and you can kind of see that right here. You can kind of eyeball that. So if the pass band is at 0 dB, then the stop band, just kind of eyeball this. And it's hard to get accuracy of 13.5 dB by eyeballing this, but you can at least say, well, gee, that's probably pretty close to 13.5 dB down. And mathematically, you can show that. It also says that there's some frequencies that get eliminated. So basically, 2 pi over n gets eliminated, and integer multiples of that get eliminated. So it's another kind of easy way if you really wanted to null out a couple of frequencies. This is a very easy way to do it, and still have a low-pass filter. So it all has this other advantage. Again, you can pick n to null out whatever frequencies you might want to null out. Go ahead.
Could you repeat what null bandwidth is?
Null bandwidth is the bandwidth means extended positive frequencies. The null bandwidth means where's the first point that the magnitude goes to 0 in linear units.
Kind of like bandwidth starting from 0 Hertz, going as far as you can.
That's right. Now, we can also call it the null-to-null bandwidth more generally if it's bandpass. Right. And so if you look at this, this is from 0 to pi. You can see this is normalized to pi. So this is really pi here. And so there's going to be a mirror symmetric version of this as best as I can do it. Close enough, I guess. So this, so again, this is, bandwidth is extended positive frequencies. If I were to modulate this, right, then I could talk about the null-to-null bandwidth as a bandpass filter. And we did this in earlier homeworks when analyzing the finite length sinusoid. We multiplied by a rectangular pulse, which gave us a sinc pulse, a sinc function in the frequency domain. And so this is just a sinc, right? This is a rectangular pulse in the time domain. Fourier transform is some sort of sinc, and this is the magnitude response of that in dB. So it doesn't have quite the sinc shape you'd expect because we're in dB and not linear units. Okay, but these are just the zero crossings of that sinc. We're just in discrete time. All right, first order difference, or first order differentiator. So it's a discrete time approximation to a first order differentiator. And, again, the input-output relationship here is just simply, y of n is the current input value minus the previous input value. Very simple to implement. No multiplications, one addition, one subtraction, one memory location to keep track of the previous input value. This has one 0 location and one artificial pole. And you'll notice the 0 location is right here at z equals 1 or omega equals 0, right? So this is z equals 1, which means omega equals 0. Remember, omega is the angle with the positive real axis. It means that the 0 frequency is being eliminated or not passed through the filter. And we've seen that we'll see that in the magnitude response. And we've already seen it in the mandrel demo. So the filter is bibostable. because the pole is inside the unit circle, or again, the region of convergence, if we include that here, z does not equal 0. So again, the region of convergence includes the unit circle. We're bivostable, but we know this in general about FIR filters. Any FIR filter, every FIR filter is bivostable. It's an easier answer on a test. That you just say, yeah, all FIR filters, unless I ask you to somehow prove that or demonstrate that analytically, but you can state that as a fact. All right, so the frequency response, again, because we're bivostable, we just substitute z equals e to the j omega and plot the magnitude and phase using freq z. And so here again, it's not, again, the world's greatest filter. It's not, as I say, it's not the most frequency selective filter out there, certainly, but it's easy to implement. And the shape is a little bit harder to describe. We certainly eliminate frequencies. We certainly eliminate zero frequency or DC. Right, that's gone. And we pass a lot of other frequencies, pass, and there's a little bit of gain above 0 dB because we didn't normalize. We didn't use half as the coefficients. It's okay. We can always normalize it if we need to. Now, phase response looks nice and linear. Right? No discontinuities except at the origin, which you're not seeing here because we don't plotting non-negative values. But this is just a nice, and the slope should be minus 1/2. Again, we put this in radians. This is in phase. All right, so back to selectivity. This, the best choice out of the 4 I gave you, which was low pass, high pass, band stop, band pass. You could say it's a notch because it removes 0. You say it's band stop. That's probably not too far off. That's pretty accurate. High pass, in my view, is probably the best answer. But again, it's one of these things on a test to justify your answer. It's certainly FIR notch. It notches out 0 frequency. Okay, now some infinite impulse response cases. We'll have to figure out whether they're filters or not. So here's a system, an LTI system, provided the initial condition 0, that gives us an infinite impulse response. So again, the input-output relationship for this one. This is just the running summation. So I take the previous output, and I add it to the current input. So this is recursive feedback. It relies on previous output values. And we did this on homework 1.1. So here's the transfer function. I have 1, 0. I have an artificial 0 at 0 because it can rewrite, again, I can multiply numerator and denominator by z, and I get this form. So multiply by z over z. So if I multiply this by z over z, I get this form, which is valid as long as z isn't 0. So either way, again, the z to the minus 1 is nice because it maps to an implementation to a delay block by 1 sample. But I prefer positive powers of z when finding roots. So both are useful. Okay, so I have one pull at omega equals 0. Right? So I have a pull at z equals 1, which is omega equals 0. So now the problem is that this is not a bivostable system because the poles are not inside the unit circle. Or you can also say, what's the region of convergence here? What's the region of convergence? Greater than 1. What is greater than 1? Absolute value of z. Yeah, common mistake on tests, z's complex. We need to figure out, we need to make this a scalar value somehow or a real value. So it's really, remember, absolute value of z greater than 1. Geometrically, visually is what? How would you describe that? everything outside the circle of radius 1, right? So the region of convergence would be, all this stuff out here, outside the circle of radius 1, but not including the circle of radius 1. It is an infinite impulse response LTI system. My preference is not to call it a filter. It is my preference, my personal preference. When I think of filter, I think of something that's bivostable. But I may slip up every now and then, right? And we'll talk about that. You can use this as a filter if you're careful, right? And that's later in the solution of this. So we can use it. So let's look at the frequency response. Frequency response is a little bit tough to get to from the z domain because we cannot directly substitute z equals e to the j omega because that's the unit circle, and the unit circle is not in the region of convergence. So again, the region of convergence tells us for what values of z is the z transform function valid. And we're excluding the unit circle here. So we can use a discrete time Fourier transform. I gave that hint on the homework hint. So we can do that and look up the Fourier transform, the discrete time Fourier transform, of the unit step in the textbook, online, and we get this. So we get kind of what we expect, which is the term that we would have gotten if we had substituted z equals e to the j omega. But you'll notice that this term has a real problem at what frequency? Yeah, when omega is 0, I get the denominator is 1 minus 1, which is 0. I get 1 over 0. That's, that's not so valid, not very valid. So what happens at the origin is represented by the direct delta. Here it comes again. And this direct delta is periodic with periodicity, or this is now an impulse train, with periodicity of 2 pi. So in the period from minus pi to pi, we just have one of these, and that's located at the origin. So if we want to plot that, it's a little bit tricky because MATLAB doesn't usually let us deal with this cleanly. So what I can do is plot the part that doesn't blow up, or at least plot it over frequencies that it doesn't go to infinity in value. So I plot the first part of this, but I don't include omega equals 0. And instead at omega equals 0, I put in the direct delta with area pi. A little bit strange. Now we can use this in filtering because it works just fine over most of our frequency band of interest. It has trouble at 0, and it's also going to have some trouble around very small values of omega, like 10 to the minus 5 or 10 to the minus 8. This gain just gets incredible. All right, so what we can do, what kind of filter would you put in front of this? Go ahead. A notch filter, like the one we just did, part B. So put the notch filter ahead of this, which gets rid of 0 frequency completely and attenuates frequencies around 0. Put this first, and then this one. Now the cascade is a filter. Yeah, hang on. It's on the same page. Yeah. So again, this is the magnitude response of the two-tap first difference, or first order difference. It eliminates 0. So if I put that filter first and then the integrator, we're fine. Right. Now go ahead.
Why would you put the notch filter and that filter together? Wouldn't that just attenuate everything?
Well, it doesn't, and what happens is this. Again, if I were to use a normalized, what I really just need is to notch out 0. I don't have to use this filter. But any filter that gets rid of zero frequency is helpful because that's the frequency that the integrator, discrete time integrator, has trouble
So
with.
it's like you eliminate zero, but maybe not the frequencies that are very close to zero.
You don't eliminate, but you want to reduce because you also have trouble in the. This is now back to the discrete time integrator. I have trouble at frequencies very close to zero because the gain is just too high. So if I use any, I use 16-bit data or whatever, I'm going to very much saturate my 16-bit value here. And it's not all that useful. So I really want to get rid of zero completely and attenuate frequencies around zero and then apply this filter. And we do this in practice. And sometimes the integrator might be applied to a bandpass signal anyway. I mean, it's very possible that that the signal itself is already somehow doesn't have a DC component. Okay, fourth example was the causal bandpass filter with center frequency omega naught, and omega naught was a parameter, what that frequency was. But I told you I asked you to put the poles inside the unit circle. And I did this by specifying the pole radius of these two pole locations to be R. And R was between 0 and 1 inclusive in the problem statement. So again, the poles are inside the unit circle. We should have bibo stability. Here's the pole 0 diagram shown for omega naught equals pi over 2. So you can see that. So here's your pole location. And I'm not sure what radius that is, might be 0.9. Yeah, there we go. So the radius is 0.9 and the frequency is pi over 2 just for the plot. Bibo stable, get the frequency response by substituting z equals e to the j omega. Plot the frequency response using freq z. Okay, and it's a bandpass filter. And, again, I could multiply by the right constant to get the peak value to 0 dB, just a scaling issue. But it is a bandpass filter with about 20 dB of stop band attenuation. Right? So if you look at the stop band attenuation, about 20 dB. Okay? And the closer, and we'll see this in demos later, if I make that radius larger, like 0.95, I get a greater stop band attenuation. So I can pick my value of R accordingly. Okay, any questions on problem 1? Any more questions on problem 1, I should say? Okay. Very useful filter. Right? This is a filter that's tuned to a specific frequency. And the bandwidth can be made as narrow as we want by pushing the pole close to the unit circle. I can make R 0.99 and get a very narrow bandwidth and a lot more stop band attenuation. So there's a configurability here, and it's very useful. It's a very simple filter to try to pull out a frequency value from a signal. Go ahead.
When you cascade the integrator,
Yes. You get the identity, so it's not as useful as one would think. That's right. So you want a different, so the intuition is correct. So if I cascade a first order differentiator with the discrete time integrator, I get the identity system. That's correct. It's probably not what we want. So use some other filter to get rid of zero frequency, and not the first order differentiator. Okay. This was problem 2 was to filter a gong sound provided in the Johnson Saris incline, and so for those listening on video, there's a bit of description at the end of the solution set on how to get access to those MATLAB files because it's free. They're not copyrighted for a reason. The authors wanted to allow the files to go out with the largest and widest possible availability and dissemination. So the gong sound is there in those files, and so are the MATLAB files to process the gong wave file. But this was an exercise in recorded sounds on your computer. It's in a wave format. You load it into MATLAB, you filter it, and you can save it back in wave format and play it if you want to, or you can play it directly from MATLAB. So we have a gong that used some Fourier analysis to figure out where the main frequencies are. The problem tells you there are 3 of them. 520, 630, and 660 hertz. And then the problem asks you to design a low-pass filter to pass 520 hertz and attenuate 630 and 660 hertz. Now, I could have done a notch filter here. I could have asked you to do a notch. The right averaging filter may have been able to do this. There are other ways to do a notch. We'll talk about that soon. But anyway, it's just a nice exercise in designing a low-pass filter and applying it to a signal and listening to the result of that low-pass filter. So I'll show you visually. So we designed the filter. So here's the Gong waveform as it is. Here's the Gong waveform after filtering. Here's the frequency components over all the Gong sound. So it doesn't tell you when those frequencies occur in the time domain. It just tells you on average how much strength is in each frequency, bin or range. So we have peaks at 520, 630, and 660 hertz. All right, so here's 520. And we've got 630 and 660. Apply the low-pass filter, and the net result is that the content at the frequency components at 630 and 660 have been attenuated, not as audible. And the higher the filter order that you use, the more attenuation there will be using a Parks-McClellan design. And the Parks-McClellan design normalizes the coefficients, so the pass band is centered at linear units of 1 or 0 dB. So you'll see there's no change in the high end of this. Okay, so the vertical axis is the same. The vertical axes are the same in both frequency plots or spectral plots. Okay, so you should have heard, in terms of an audible feature, you should have heard a pure tone dominating the Gong sound after filtering as opposed to 3 tones dominating the sound. Depends on your filter. But if it was done, and so how long does the filter need to be? Well, it could be short enough if you happen to get a notch right in the middle of this. So you might actually get a short filter might actually pull it off, but more because the notch would just happen to be at the right location in the stop band. But more generally, you want a long filter. So what orders did you use for filter lengths for this one? 100.
Yeah, it's a fairly large number.
Okay, 100 seems large. It does. It's not large by what we do in practice. So it's going to seem like it's a lot of coefficients, but in the end, it's like 100 multiplies, right? For 100 coefficients, 100 multiplications per sample. It's not a lot of multiplies, really. So FIR filters in audio can go to 512, and I've seen filters as long as 10,000 samples of coefficients. It's FIR. I mean, we don't have to worry about stability. We get linear phase. Okay, so a longer FIR filter means more multiply addition operations per sample. So as long as we have a processor fast enough, it's not a big deal. Right? We can keep up with it. Now, at some point, we run out of processing speed. So there's some realistic limit. Length 100 is pretty common on the small side in some applications. Now, for image processing, this would be a really long filter if you gave me a 100 sample in one dimension, because it means it'd be 100 by 100 if we included the other dimension. Now, that's really large. Now, for image processing, the filters tend to be small. 5 by 5, 7 by 7, 31 by 31. 7 by 7 means 49 coefficients. 31 by 31 is a lot more than that. Okay. So they can get bigger in terms of total number of, but a lot of the stuff in image processing is smaller filter sizes, at least in one direction. Okay, that's all right. So part E is I asked you to downsample, and we're going to use downsampling a lot in the class, and we'll also use the dual of this, which is upsampling. So downsampling by 2 is a way to Well, lots of reasons we downsample. Can you give me some reasons why we might downsample?
Modulation.
Yeah, I can actually do demodulation with downsampling and the appropriate filtering. That's true. What else can we do with downsampling by 2? Or downsampling by 3 or 6 or 10 or whatever?
Reduce the size of your signal.
Reduce the size, absolutely, reduce the number of samples per second. You're changing the sampling rate. So by downsampling by 2, which we can do very easily in discrete time by keeping every other sample, I can now change the effective sampling rate. I can reduce it by a factor of 2. So the rate at which I have to then process the signal is cut in half. Or if I downsample by 10, it's reduced by 10. Because I have a factor of 10 fewer samples per second to process. So it's a good way to reduce complexity. We do it for that too. What's another reason to use downsampling? Where else might you want to change the sampling rate of a signal?
If you're like transporting it, maybe.
To transport it?
So it's smaller, like size of the actual file.
I can transport it, so I can also reduce file size, which is kind of what I did here, is I reduced the vector length by 2.
If your hardware doesn't have like the sample rate that you found rather than
Exactly. So the hardware doesn't support the sampling rate you want, so you change the sampling rate that you have to what you can use. Another way to say that is I can change formats. So if I, for example, audio has lots of different formats, different sampling rates. If I wanted to convert, say, 48 kilohertz sampling, so think about audio, and I want to convert, so I can do format change, and I want it to convert, so format change, and I want it to convert, say, sampling rate 48 kilohertz, which is a common audio sampling rate, to a common speech sampling rate, 8 kilohertz, what downsampling factor would I need? 6. So for every block of 6 samples, I keep the first one. Next block of 6 samples, I keep the first one and throw out the rest. And that will change the sampling rate from 48 kilohertz to 8 very efficiently. That's the good news. Bad news is I get some amazing distortion that can happen if that's all I do. And that's the rest of this problem. There was another handout I missed.
I was just going to say expand the frequency spectrum. So in other words, we're just shifting the frequencies.
That's right. You can expand the frequency spectrum by doing this. And so if we look at what happens, so again, here's the MATLAB code to do it. It's pretty simple in MATLAB, but don't let the simplicity of MATLAB necessarily mean it's simple in an embedded real-time implementation. Those are two different things in many cases. But at least we know that conceptually this is not so difficult. Now, so what I ask you in this case to do is apply the downsampling operation by 2, but keep the sampling rate that you actually play back the audio the same. So the length of the signal now is half as long as it was before. And this causes a aliasing to occur, and you see the alias version from the downsampling. Go ahead.
Can you use upsampling the same way as this, where it lets you essentially make it look like a different frequency and possibly distortion?
That's right. The question is, can you use upsampling the same way? Absolutely. So you use upsampling the same way. You can do rate changes, but now you are increasing the rate at which you now need to process the signal. But the other applications hold change of format. You get an interesting effect in the frequency domain. You get artificial high frequencies introduced, and that is a form. It's similar to aliasing. It's called imaging. We'll get to these issues in lecture 4.
I was going to say, well, if you did upsampling, would you end up making the sound a lot lower because now it takes more time to reach those samplings?
That's right. So if you upsample, it's going to sound lower. That's right. But you also get some artificial high frequencies thrown in as well.
Oh, I see.
Yeah, it's an interesting effect. So it's worth trying. I almost added this to the question, but it's very simple. It's 2 lines of MATLAB code to do the upsampling. To insert, how do you upsample by 2? Every sample that comes in, you write it to the output, and you append a 0. Next sample comes in, write it to the output, append a 0. So you're inserting a 0 between every pair of samples. And this now creates artificial jumps in the time domain signal, which corresponds to high frequencies that weren't there when you had the signal the first time. Okay. All right, so that's problem 2.2. So all kinds of fun with audio signals. You can run it through a squaring block and see what happens. Frequencies double.
So
and also go to DC. It's great. We don't hear DC. Go ahead.
That like effectively slow down the audio if you were to upsample it.
Yes, you can if you upsample if you upsample and play back at twice the rate. So it'd be you'd speed up the audio.
Yeah.
Downsampling, if you downsample by 2,
Either way around.
get this straight. So if you downsample by 2, you're yeah. Okay, so let me get the math. Yes, let me get the math on this just so we. All right. Right. So if you remember sampling a sinusoid, at sampling rate FFS, then the conversion to discrete time frequency So now if I were to do downsampling, so this is my x of n. Now if I look at, if I do downsampling, then what happens is y of n, after downsampling, this is x of n, is x of n divided by 2. Is this right? Yeah. No, it's 2. Sorry. I'm downsampling by 2. Okay. So that means that I only keep every other sample in x. So when n is 0 for y, x of 0, y of 1 is x of 2, y of 2 is x of 4. Right, so I'm keeping every other sample from x. If I put that into x of n, I get the following. And this was an old test question on our midterm, by the way. It's in the reader. Okay, so now I multiply by 2n. Now I can look at this a couple different ways. Either, if I keep the sampling rate the same, I double f naught. Right? Or, if I keep f naught the same, I have to reduce the sampling rate by 2. So I can write this as either cosine 2 pi 2 f naught. So if f naught is really large, I get aliasing. I get a doubling, and then I might also get aliasing. And this is also equal to cosine 2 pi f naught fs over 2 times n. Right, so this is either I have the sampling rate, I play it back at half the sampling rate, f naught stays, or I play it back at the same playback rate, and f naught doubles. And it may also alias. If 2 times f naught is greater than half the sampling rate, I have aliasing. Or if it's equal to half the sampling rate, I have aliasing. Okay, so if I downsample by 2 and I play back the audio at the same rate, it's half as long. Right? If I upsample by 2 and play back at the same rate, it should be twice as long. All right, let's move on to 2.3. Now, I did a demo in class about using the filter design and analysis tool FDA tool in MATLAB, and I showed that when you use the Parks-McClellan algorithm, or the Remez, or it's also called equal ripple design, lots of names for the same method, it doesn't always meet the specification. And that may bother you, and it bothers me a little bit, but I'll tell you where it came from. There's an estimator, given the magnitude constraints for Parks-McClellan, there's an estimator developed by Jim Kaiser, same Kaiser as Kaiser Window, that estimates the order you need, the minimum order. And it's an estimate based on designing lots of filters. It's an empirical formula. It's pretty good, but it's not 100% accurate. Maybe it's 10% error. Typically good enough for us in engineering, but we also have to make sure then we have to make sure that the filter that comes back is actually meeting the specification. And more generally, we should do that when using software. So again, here's the spec. It's a bandpass filter, bandpass 6 to 40 hertz, stop band 0 to 1 and above 45 hertz, sampling rate of 200 hertz. So doing the Parks-McClellan, as I demonstrated in class, using the minimum order option doesn't meet specification. So in the stop band, it exceeds the 40 dB down that we have requested or trying to meet. We get 37 dB, or a little bit less than 37. And because we're basically 3 dB off, what we can do is increase the target stop band attenuation in the first and second stop band. We can increase that by 3, knowing that we're basically off by 3 here. That's where I got the homework hint from, or what I used for the homework hint. So if I'm off by 3 dB here, then let's just increase what I'm telling it to do by 3 dB, and let's see if we get something that works. And it does. And we get an order that's 60th. That's wrong. Whoops. That's the next design. All right, so we get, with a little bit of, with changing what we tell it can be different than what we really want. What we want to make sure is whatever filter comes back meets what we want. We can tell it something different, as long as the design meets our original filter specification. So there's a user specification, which can be different from the design specification. We just want to make sure that the design specification is met. So if we, again, by 3 dB increase, we get a filter of order 60. So there's 61 coefficients. And you can zoom in to pass band and stop band, and we're fine. Right, we're within the plus or minus 1 dB in the pass band, and we're at or below 40 dB down in the stop band, in both stop bands. Phase is linear except for the points of discontinuity corresponding to zeros in the magnitude response. Least squares method. Now this one's really not so intuitive an FDA tool to use. So in the hints I say go off and maybe use the FIR-LS command. So I give you both answers here. So I went and ran an FDA tool. It took me about an hour of iterative stuff. And I got down, and I'm not saying this is the absolute minimum order, but I got down to an order of 72 to meet spec. And I had to, and I mentioned this, I think in the hints, the method has real difficulty in meeting the specification at the stop band frequencies. So to make it work, you move the frequencies you care about into the transition band. And it will, so if it misses in the transition band, who cares, as long as it gets it right in the design spec frequencies. So I moved in the stop band from 1 hertz to 1.5, so it's in the transition band. I moved the pass band from 6 and moved it into the transition band, which means 5.5 hertz. I moved the upper pass band frequency into the transition band, the lower stop band into the transition band, and then you got to play with these weights. I mean, this is a lot of work to get there. And as you might guess, well, we're just going to use the Parks-McClellan, and you'd be right. So the Parks-McClellan algorithm, which is done by Jim McClellan and Tom Parks. And Jim's at Georgia Tech, and Tom Parks is retired from Cornell as faculty, but they did this work at Rice. McClellan was the PhD student, and Parks was the PhD advisor. So this is going to give us the shortest, the Parks-McClellan algorithm gives us the shortest linear phase FIR filter with real coefficients. But the downside is I have to search for the minimum order. I know kind of what it is, 10% error, but then I have to search for it. But it's going to be once I find it, it's my smallest one, which is great. That's the good news. There is some bad news, as you might guess. All right. I'll tell you, the bad news is if the filter length is too large, over 400, the Parks-McClellan algorithm, as implemented in double precision, sometimes will not converge to an answer to find the coefficients. That's the bad news. All right. And least squares has the same problem, actually. Okay, anyway, so here's least squares at FD8 tool. It's really clunky, and anyway, I found an answer. Or you can use MATLAB code, and the MATLAB code looks a lot like what you did in 2.2, and designing the Parks-McClellan filter for the Gong sound, low-pass filter for the Gong sound. Very similar story. You know, find the Nyquist frequency, set up the frequencies of interest, the ideal. You know, 0 means stop band, 1 means pass band for each frequency value, and then just run it and iterate. And order 77 met spec. Kaiser window. Kaiser window, for some reason, didn't meet spec, and I'm not sure why that was for me. So the original, again, it's an order estimator from Jim Kaiser for his own Kaiser window. FDA tool gives me an order of 90. That didn't meet spec. It missed here at DC, the first stop band. It was okay here, but you know, it missed down here around 0. Order 98 works. We'll fill in the last pieces before we go. So part B was the impulse response for Parks-McClellan. Order 60, 61 coefficients. And you'll notice the nice even symmetry about the midpoint. So there's the midpoint. There's the sound of DSP in the classroom. Good. All right, so here's midpoint, and you'll notice the even symmetry and the impulse response. Here are the filter types, order and length. And then the last piece was, so which one would you go for? Well, Parks-McClellan, if you got it. I'll give you the shortest version, shortest filter. And then part D, you know, we're just implementing a difference equation, right? So the FIR filter looks like, here's the output, and the input is just a bunch of multiply adds, right? It's right, so we have H0 times Xn. We have H of 1 times X of n minus 1. We have H of n, and so forth, right? So it's just multiply, add, multiply, add. So if I have capital M, if I have capital N coefficients, I need n multiplies, 1 per term. I need n minus 1 additions. So it's an order n operation for every input sample to produce an output sample. We have to store the coefficients. So that takes n words of memory. To store the coefficients, I need to store, so this is n words. To store h, I also need n words to store the previous input and the current input value. And I'll do that in a circular buffer, so that when a new input value arrives, I can just stick it in the circular buffer and keep going. So the total storage is 2n words. And the number of multiply accumulates is n. Okay. See you next time.